All right, everyone, welcome back to System Software. So now we are going to start our implementation of the compiler. So we went over a really brief crash course in parsing. We looked at the intermediate language that we're going to be compiling to assembly. So, and don't forget tonight, you have the calc project due, and that's just copying, hand typing out code so you can get your environment set up for the compiler framework. Questions on the kind of concept of parsing, questions on our intermediate language. I've also released the first project description, and we'll go over this more next time, but you'll be compiling part of our intermediate representation to assembly, and this part will just be for function definitions and function calls. So no parameters, no local variables, just functions and function calls. The code for this is pretty short, but there's a lot of subtlety to the assembly to doing this. We'll start going over today, this notion of functions and how they actually get implemented on the machine, because the C language notion of a function is not quite supported or is not directly translatable into x86 assembly code. Okay, so let's get started. All right, so first let's start off with the kind of same question you always hear in every class. What is a function? What is a function in programming languages? Yeah.
A function that basically encapsulates some code, so we can.
Okay, that's a good word. Encapsulates code.
You can use it like multiple times without having to rewrite the same code.
Yeah, and how do you call it?
By passing some arguments to it.
Well, how do you identify that encapsulated piece of code?
Its address and memory.
Well, do you actually specify an address when you call it? Yeah. It's name. Yeah, it's name. So yeah, that's a perfect definition. You have encapsulated code, some computation, that's named. And the benefit of that is that you can call it multiple times. You don't have to rewrite the code every time you do it. And a function is really a method of abstraction in code. You can add new terms to your language. So if you think about C, you have several keywords like if and while. But with functions, you can actually add your own names to the language. Just like with variables, you can add your own name. And that name is not just storing some memory like a variable, storing some data like a variable. You can actually name a computation, add it to the language, and now you can use that name whenever you like when you're writing code. And so that's kind of a nice definition of a function abstraction. It encapsulates a computation. And in C, at least, it's defined by a name. There are other languages that have anonymous functions. And also, as you're getting at, also its input and output. So a function is not just a named chunk of code, it also has I/O. Does anyone know the term for a function-like thing, a named piece of computation where you don't have an I/O specification? Yeah.
Is it a macro?
Oh, okay, that's a good one. So macro is sort of like that. Macro is really just text replacement. It's subroutine. Have you ever heard the term subroutine? So this is like old school language implementation. But a subroutine is like a function, except there's no real I/O specification. It's just a name, a label, basically a branch to a section, lines of code. And this I/O behavior and the way functions handle this actually sets it apart quite a bit from a branch or a subroutine, which is what we'll have to deal with in our compiler. Yeah. Oh, subroutine? Yeah, sure. So if you've never, this is more like old school computing. Subroutine. So you don't really see these called out very much in current languages. The kind of abstraction you use for encapsulating code is functions. Pretty much all popular programming languages have some function abstraction. And you're probably very familiar with their behavior because you've written C. But how does it work? When you make the call, you give the name, you put the input values that you want to pass as input parameters, and then the caller freezes. It stops executing, right? And it waits until this function has completed execution, and then it comes back to the caller, and then that returns its value, and then continues running. So this is probably all really obvious to you. You probably know this. But if you think about some other behavior, like our fork system call, it worked in a similar way, but then we had multiple processes, so we didn't get this blocked freezing state. There are also functions, non-blocking I/O functions in the kernel level. But functions in C work like this. Transfer control to the callee function, the caller freezes, we give input values to that callee. The callee does some computation, computes a return value, passes it to the caller. That function's done, and then the caller can resume exactly where it left off. Questions on that? So this feature, this ability to freeze the state of the caller, because when you're running this, when this caller function is running, it's operating on memory, it has its own variables. And that stays sound. That doesn't get messed up by your caller function, callee function, unless you want it to, if you have pointers, for instance. But the abstraction preserves this state of each function. So let me give an example of what this looks like. So here's a set of three functions. We have main. Main prints out the result of calling f and passing 3. F takes in one parameter, passes that parameter to G, adds 1 to it. That call to G, it takes its parameter and multiplies it by 2, returns its value. Questions on this example? Okay, so when we call main, main calls f. F has a variable a that it holds as 3. And f also calls g, and it has a value. When g is called from f in this program, what's the value of b when it gets called?
6.
The value of b when it gets called. So 3. So a is 3 here. When we call G, A gets evaluated, and C, A gets evaluated, and that's used as the input parameter to G. So when we first call G, its input parameter is named B inside of its own function, and so that B gets assigned to whatever its caller passed it as input. So B is also 3. Now what happens, what's the return value? So when this G returns, what value does it compute? Yeah, compute 6. And so when we get back to this call here, we can just think of that call being replaced with its return value. And then F computes its return value, which is 7. And inside of the call to f of 3, that gets replaced with whatever its return value is. Questions on this? Yeah.
What would this look like if you're dealing with void functions?
Void functions are not meant to have return values, so it would have, it would be a void value. I think it would probably be a compile time error in C. It would probably say you can't assign a void value to something. But any questions on this? Just the kind of basic semantics of a C function? Okay. All right, so let's see how this actually gets implemented. So let's say instead of having a local variable, we had x here as a global variable. what's the return of, so if we call f, I didn't put the main function here, but let's say we call f. We run f, what gets printed out? So we assign x to 1, we then assign y to whatever the return value of g is. We print x, we print y. G assigns x to 2, returns its value. So what gets printed out?
1, 2.
Okay, who says 1, 2? And you had a different answer. 2, 2. Who says 2, 2?
Oh, yeah, it is.
Okay, so let's walk through it. And we can use our diagram here to keep track of our state. All right, so we've got this global variable x. We have some variable y, which I didn't even declare. All right, when we call f, it assigns x to 1, so x gets 1. It assigns y to whatever the value of g is. But in order to compute this, we need to freeze f state, because it has its own state. It has a position that it's executing at. If it has any local state, it has local state. And we go off and we compute g. So we go to compute g, what does it do? It assigns x to 2. So which x gets modified? The global x. It's a global x that both f and g have access to. So this x here, this global x, gets updated to 2. And we return 2, although nobody's there to accept the return value. We return, and we return exactly back to the place where we left off, or strictly speaking, the next assembly instruction. And this, what's the value of g? Here? So we return to, it does get used, so 2 gets returned here. And what's the value of the call to g after we complete executing it? 2. So what's the value of y here? Also 2. Did you have a question?
Yeah. What if you declared x like x is 2 inside of g?
Wow, well then it would be quite different, because then it wouldn't be
It would be a global.
it wouldn't be a global variable. And that's exactly the point here, is that when you have a global variable, these are really just subroutines. There's no local state to these functions. It's no different than just having a branch in assembly. But okay, let's finish it out to make sure everybody's clear. So then we've got a print statement, print x, print y. So what's the value of x when we print it here?
2.
It's 2. What's the value of y?
2.
Also 2. So those who said 2, 2, you're right. Those who said 1, 2 were probably thinking, well, this x, you're used to having variables being local to functions. So it must be 1, 2, because x is local. So you're probably already, thinking of the function abstraction in your head without realizing it. Okay, so this is exactly what your fellow student asked. He said, what if we have function local state? Just to make sure everybody's on the same page, let's go through this. So the only difference with this version of the program, it's the same program except x is now declared inside of f and g. There are actually 2 versions or 2 different x's. So let's just make sure we're all on the same page about how this program executes. All right. So inside of f, so let's start executing f here. I assign x to 1. What happens to x? Okay, which x?
1F.
The one in f, yeah. So we can think of our memory as now being divided into variables for different functions. They can have the same name, but they're actually different locations in memory. And so you could actually even draw out your RAM and say, all right, well, this is f's x here, and we can make a separate space for g's x. So they have 2 different memory locations. Somehow, this is going to have to happen, right? It's going to have some different memory locations for these. Okay, so we assign x to 1. Which x gets assigned to 1? F's x. And then we have y equals whatever the return value of g is. Let's make a space for f's y here. So how do we compute the value of g? Pause, yeah. Yeah, we pause the execution, and we start computing the value of g. All right, so g is now going to assign x to 2. So which x gets assigned to 2? G's x. So f's x stays 1. And so I know this, for some of these probably seems like very simple, right? Like you can figure this out on your own. But how this is actually done, we're going to learn how we actually, because the assembler will not do this for you. Your compiler has to be able to manage memory automatically for you. All right, so x is 2, g's x is 2. We return x, which is 2, and resume control back here, replacing g with 2. So when we print x and then print y, what do we get? Which x gets used here? F is fx, which is 1. So we print 1 and we print 2. Questions on this? So because you've all learned C, you just sort of know about scope. You know that because this x is declared within f, you know that all x's that appear within the body of f all refer to this x. And you've been trained, you've learned that if you see an x used in another set of curly braces in another body, that's a different x somehow. Even though they have the exact same name, they're actually a different x. And now, using that is pretty straightforward once you learn it. The trick is, how do we write a compiler that will generate assembly code that will manage this for us? Because remember, what does x mean to the machine? What's the x representation of x here in this text file? In this text file, what is x? It's an ASCII symbol. So this has zero meaning to the machine in terms of its computation. So it's the compiler that needs to interpret this and create a memory location for it. So sure, when we write the compiler, what we're going to do is we're going to associate these symbols with memory locations. But there's nothing intrinsic in the source code that does that. It's the compiler that will create that behavior, that will create that semantics, that will specify that semantics. All right, I know this is probably seems like really rudimentary intro to C, but questions on this behavior? Yeah.
For compiler behavior, will you have to account for cases where you declare multiple values at once? For example, int x, y, z, a.
No, the syntax, no. So simple IR, it's an intermediate representation. We don't have any of those. So that's just syntactic. So there's nothing different about that. Syntactic sugar, so to speak, for int x, int y, int z.
So we will only use the intermediate language to assembly.
Right. You only do intermediate language assembly. You won't have to compile C, the intermediate language. It'll be much easier. If you're interested in the full compiler toolchain, take my compilers class next semester. If you're interested in doing that. But yeah, we're going to have a much easier task. But in order to compile functions, so functions are C-like in our IR. They're not assembly-like. So you're still going to have to implement the behavior of C-like functions in your compiler. Okay, so that's local state. Functions have local state. And you can think of that as separate memory locations for all of the local variables to that function, even if they have the same name. Each function gets its own allocation of variables. Okay, let's look at the second, yeah.
Does it work the same with recursive calls?
Very good question. Very good segue into my next section here. So what happens when we do this with recursive calls? So we've got a nice, so let's see. Yeah, so in this example, I have a statically allocated variable here. So it's function local, but it's actually, so statically, you can think of it as global. It has its own local variable, but we'll see what this looks like when we go to run this static function. Okay, so this is a classic factorial with a little bit of a modification. Let me get a new page here. All right, so let me just walk through it to make sure we're all on the same page. So this factorial takes one integer x as an input. It declares a local variable that is local to itself only. So if there's another old x declared somewhere else, that's going to be a different memory location. It has its own memory location for this x. We'll talk about static in a second. If that x is less than or equal to 0, we return 1. It's my kind of lazy error handling. Otherwise, we copy the x for some reason. We copy it to this old x variable, and we decrement x. Maybe it's not the best way to write it. This is the way I wrote it. And then when we compute the return value, we return whatever that old x was multiplied by factorial of the new x. Questions on the algorithm? I know you might question why I wrote it this way, but questions on the algorithm. Does it compute factorial? Okay, let's see. Let's see what it computes. Okay. All right, I'll just lay out the memory here. So we've got a space for old x. We've got a space, well, let's give a space for x first. We've got a space for x. We've got a space for old x. And yeah, that's all we need. We've got a space for x and a space for old x. All right, so let's say we call f factorial of 3. I'm just going to say f of 3 because I'm lazy. So f of 3. When we start executing factorial with f of 3, what's the value of x? 3. Okay. So then I go to this line here, x less than or equal to 0. Is this true or false? It's false, so we go here. What does this assignment do to our memory state? Yeah. Okay, so old x is 3. And now x equals x minus 1. What happens to our memory? X becomes 2. All right, so in order to compute old x times factorial, let's write this down so we don't forget it. But yeah, so what's the value of x here? It's 2, so we call f of 2. Old x, we know, is 3, so we're going to be computing 3 times whatever the result of f of 2 is. So what do we have to do in order to compute, in order to figure out what this value is? Yeah, and regardless of whether it's recursive or not, we just have to call this function, which means we pause the state of our current call and go off and start executing kind of another version of factorial. We just start running from the top of factorial. Okay, so when we do f of 2, what's the value of x when we do f of 2? It's 2, so this variable stays the same, this value stays the same. And is x less than or equal to 0? No, so we go down to old x. All right, so what's the value of old x here? It's 2. All right, so now old x is 2. And what's x here? 1. All right. So then we've got to compute old x times f of 1. All right, then we compute f of 1. Same thing happens. X is already 1. Old x gets turned into 1. And we'll call f of 0. So f of 0 finally triggers our return of 1. Okay. So here is code version of our factorial function that I've implemented. Okay, so when I run factorial here, I get 1. And the reason is that every time I'm calling factorial, I'm reusing the same state in memory. And so this blows away the previous old x that I had. Sorry, I just want to confirm something, that this actually works when you take out static. So anyway, so the fact that we're reusing the same state every time,
What do you mean the same state?
what's that?
What do you mean the same state every time? Like between function calls?
Sorry, I think I made a little mistake here. So I put old x first. I think old x should be second. I think, let me just double check. Okay, so sorry about this. So let me make this clear again. So the problem is that when I go to call the next f, I reassign old x inside of f. So let me walk through this again. I think the reason it was happening was because of some reorderings that the compiler was doing. Let me show this code. Okay, so when I first call f of 3, let me walk through this again. So old x is assigned to 3. What's that?
X is now 2.
X is 2. When I call f of 2, old x is assigned to 2, and x is assigned to 1. When I call f of 1, old x is assigned to 1, and x is assigned to 0. So the problem is that the next thing I do after returning from f of 2 is I go to compute factorial of x times old x.
Climb back up.
You climb back up the tree.
So 1 times the old X.
So let me write this out again. So here I say old x equals 3, x equals 2, and then I compute f of 2, and then I compute old x times whatever f of 2 was, the result of f of 2. In order to compute this, though, I need to first go off and run f of 2. In order to compute f of 2, I first need to compute f of 1.
Which returns 1. Wait, no.
Well, we don't know what it returns yet until we run it. And then I need to compute old x times f of 1. But before I do that, I need to first compute f of 1. And we have the same thing. Old x is supposed to be 1, x is supposed to be 0. And then in order to compute this, I need to compute f of 0, and then finally compute old x times f of 0.
You don't have to complete that for f of 0.
So f of 0, well, we have to run the function, and we'll get 1 as a return value. Okay, so the problem here is that when I go to compute f of 0, we get 1. And what do I get for my return value for f of 1? I have old x times f of 0. What's the value of old x?
1.
It's 1. And I get 1 times 1. 1 times 1 as my return value. So that's what gets returned for f of 1 back to the call to f of 1. So we know that this is going to be 1. With me so far? So far on this? So this f of 1 is going to be 1. The problem is, what's the value of old x?
Well, that's definitely like a way down.
Well, if we had a single memory location for old x, its current value is 1. Because when we called f of 1, it overwrote old x with the value 1. Yeah?
However, I understand that, but if the answer changed, the result changed because when you made int old x, not static int old x. So would it only stay equal to 1 if you had it as static and not just int old x?
Exactly. So the static is what's doing it. What static is doing is saying, just give me one memory location for f. So f has function local state. It has its own variable called old x. But every time I call f, it's reusing the same memory location for old x. So we got the kind of behavior we wanted for this program. We got this behavior that we wanted because now there's a unique x for each function. But something went wrong when we tried to write this recursive function. Yeah. Yeah, so what we really want to do is we don't just want to have function local state, we want to have local state for each call to the function, each instance of the function. And in some sense, you could kind of rewrite this program. I'm going to do it in text. You could rewrite this program that we really want. What's that? Let me know if you work it out. I'm not exactly sure what you mean.
Like up in the arg, like arg each time like it points to a new variable.
Each call, if you have as a local variable. Well, so one way to think of this is that each call to the function is like creating a new statically allocated function. So if we had rewritten factorial to make a new version of the function, a new definition of the function for each one of its arguments. So for instance, factorial 3 would be factorial that would normally take 3 as the parameter, but if we made a new function for it, then because of function local state, we would get the right answer for factorial of 3. Does kind of make sense here? So I've made a new copy of factorial for every time I call it with a different parameter. Questions on that? Does that make sense? Seems dubious. Some of you seem dubious about this. Yeah.
Factorial 0?
Yeah, I'll do factorial 0. So factorial 0 is our base case, and it just returns 1. So first of all, do you believe that this will work correctly? All right, let me run it then. So let me run. I'll just run factorial of 3. So let's get rid of this. Oops. All right, so I've rewritten this. I've just made this new set of functions, one function for each parameter to factorial. I've left this static. So defining this static in my recursive version caused a problem because we only had a single memory location, and when we popped back up to the parent caller, that old x was rewritten with the child call. But here I've just copied the function 4 times for each version of it, and actually we don't even need the base case because there is no x here. I need to rewrite this a little more. So x is just hard coded to be 3.
Why are we doing this?
Oh, wow. So I just want to illustrate to you that when you make a function call, recursive or not, it's not just that you have function local state, but that every time you call the function, each instance, each call of the function needs its own state. Otherwise, recursion won't work. Yeah, right, exactly, in a stack. So who's heard of using a stack for function calls? Okay, so still not most people. I want to kind of get to this for those who have not learned about stack allocation yet. All right, so here is my hand-copied multiple versions of our factorial function where I make a new copy for each input parameter. So here I just hard code x equals 3 as the parameter. So now, assuming I didn't make any mistakes, which I probably did, this should give us the correct value for factorial of 3. What did I miss? Oh, they're yeah, that's okay. They don't see their own declarations. But so here we get 6 for factorial 3, the factorial 3 function. And that's because unlike when we went through our recursive version with a statically allocated variable, each function had its own copy of old x. So just like this example that I think everyone got, that each f and g each had its own version of x. So we've written 4 different functions here. They might be named factorial 3, but there are 3 different functions. There are 4 different functions. And so they each have their own copy of old x. And so this works. This doesn't have the same problem because we don't call the same function multiple times. We don't call it recursively. Questions on this? And so if you've ever had trouble understanding recursion, one way you can make it a little simpler is to think of each call to that function as not as the same function, but as a different function. So if you think of the call plus its parameters as a unique function, that might help you kind of work through recursion a little bit. Yeah. Another way to think of it as a tree of calls. So rather than thinking of it calling itself, thinking of it as a separate call, where each call is a new instance of the function. All right, questions on this? Questions on this construction here? So now doing this by hand is a massive pain if you want to write recursive functions. So what's the solution? Your classmates already said it. The solution is to have the compiler automatically make sure that there are new memory locations for every call to the function. Not just every definition of the function, but we want to make sure that every single call to the function has its own memory location for its local variables. So that we not only pause where we're running in that function, but we also freeze all of the local state that function call has associated with it. Questions on that notion? So we're going to automatically allocate new memory locations every time we have a call at runtime. And so that's not so difficult to conceptualize on paper. The tricky part is making the compiler generate code that will do this creation of memory on demand while the program runs. All right, but first let me show you what stack allocation looks like. So first of all, in C, the keyword for doing this, static is the keyword to have what we just had, where there's a single memory location for all calls to a function. That's called a statically allocated variable. The alternative, or one of the alternatives, is auto allocated. And it turns out that if you just write int old x, you're implicitly declaring an automatically allocated variable. So auto is a keyword who's seen the auto keyword? Probably almost no one, right? You never see this in C because it's implicit. Every time you declare a variable inside of a function, it's automatically, or it's by default, has the auto keyword in front of it. And auto just means it's automatically allocated memory at runtime rather than statically. All right, so let's see what this factorial looks like when we've got automatically allocated variable state. So it works as a stack, as your fellow classmates pointed out. And so here's our memory location. Here's our memory. So let me bring up the factorial function again. So this is the one I'll be looking at. Let me just get this off the screen. So here's our function again. Here's our factorial, our original factorial function. So when I call f of 3, what happens? X is assigned to 3. And so on each function call, the language runtime will allocate a fresh set of memory locations for all the local variables in that function. So this is the memory locations for the call to f given 3. So when we go to assign old x to x, or 3, this call to the function has its own memory to store those values. All right, so now let's call, and so then we update x to 2, so this updates x to 2 here. And so now when we call f of 2, what happens? We get a new chunk of memory allocated for that function call alone. And that set of memory is only for that function call, f of 2. So you see this function state for f of 3 doesn't get overwritten. Yeah?
Our integer x parameter, I mean, to make the function call, is that on the stack frame of the
Yes.
function?
Yeah, so all parameters are also local variables. And you can actually see this in the original C function declarations, which would, so this is the syntax for defining a function in the original KNR, Kernighan and Rich AC. The declarations of the parameters looked a lot more like local variables.
This is like that homework where we had to write the pseudocode of defining the parameters and locally.
Yes, exactly. So to make this really explicit in our IR, you declare local variables separately from parameters. It also makes assembly code generation easier. So all parameters are local variables in C. Okay, so when we call f of 2 here, we allocate more new memory locations for x and old x. Yeah.
So basically, each time the function is called, you're getting 2.
Exactly.
Figure out how many there are by the call.
You could figure that out. Now, in practice, we won't be able to know. It's very hard to figure out how many calls there will be while writing the compiler. So the trick we use in the compiler is to not have to know, and instead we maintain a stack. So let me show what this looks like in this call, and I'll show you how the compiler will generate code that automatically manages this state. So whenever we see a call, we just push new memory slots onto a stack for whatever local variables we have. Now we know easily how many local variables they are because we make the developer tell us. The developer tells us, like in IR, we have to list the local variables. In C, you have to declare them. So it's very easy to know statically, that is at compile time, exactly how many memory locations we need. So whenever there's a new function call, we generate code that will push more memory slots onto a stack. So then when we run f of 2, what do we have to do here? X is 2, so x is 2, and then old x is assigned to 2 as well, and then x is decremented, and so we update x to 1. Questions on that execution of f of 2? So just like before, except we have a separate set of memory locations for old x and x. Yeah? Did you have a question?
How is this different from when we have the same memory location?
So we had the same memory location. We only had 2 slots for all calls. So when we got down here to f of 1, old x and x were blown away. They were overwritten. So f of 3 wants old x to still be 3, so that when we compute, old x times f of 2, f of 3 times f of 2, this is what we want. We want old x to be 3. But because we use the same memory location for old of x, when we called f of 1, that overwrote the memory location for old x. And so by the time we popped back up the stack, here we don't have a stack, by the time we got back to continuing to execute f of 3, old x had been redefined to 1. That's why when I ran the statically allocated local variable with f of 3, we just got 1. Does that make sense? Does that answer your question?
So what's the difference between this code and that code?
Oh, so the only difference is this static keyword. So the compiler will do this kind of allocation for you. So if you say static, you're telling the compiler, I just want one memory location per function definition. When you say auto, you're telling the compiler, I want one memory location for each call. So static says one location for each definition, and auto means for each call. So this is the kind of key distinction here, is that whether we allocate memory for each definition of the function or whether we allocate memory for each call to the function. And that doesn't make a difference in a lot of cases. It may not make a difference if you only call the function once, if you don't have recursion. But if you have recursion or you're calling the function multiple times in the same, any kind of recursion really is really the only case where one of the cases where it matters, or with initialization of the variable and when you call it multiple times. This automatic allocation for each call makes the difference between having the correct execution of recursive factorial versus the incorrect one.
So then the second slide's just illustrating the auto call?
Yeah, this is auto. This is the auto version. This is the static version. Really, this is statically allocated, and this is automatically allocated. No problem. Other questions so far? So now we've executed all of f of 2, except we have to pause again to execute f of 1. So here's our call to f of 2. Here's our call to f of 1. Let me actually do this the way I did before, where I had a separate call. So f of 2, we need to go make a call to f of 2. So now here we need to make a call to f of 1. So how do we allocate memory for f of 1? We go to the stack here and we make more memory allocations for f of 1's versions of these variables. So here x starts out as 1, old x equals x, so old x gets to be 1, x equals x minus 1, so now x is updated to 0. In order to compute the result of this, we need to compute f of 0. So that's the base case. I'm going to skip executing it. All it does is test x and then return 1. So now, once we've completed executing f of 1, we can finish computing the return value. So how do we compute the return value of f of 1? Well, it's f of 0 times whatever old x was. And so because f of 1 has its own copy of old x, this is where we find the value of old x. We find the value of old x in its own memory location. Old x has the value 1, f of 0 has the value 1. So this was the same when we had statically allocated variables before. So the result of this is 1. So f of 1, its value is 1. I forgot to make a separate call here. So then in order to compute f of 2, we need to first compute f of 1. We've now determined that this is 1. So now we need to compute f of 1 times, f of 1 times whatever old x is in order to complete the execution of f of 2. So what's the value of f of 1? It's 1. We just computed that. What's the value of old x here? 2. So this is a call to f of 2. It has its own memory location for its local variables. and old x here is preserved as 2. So now we can finally complete the call to f of 2 and tell the caller that f of 2 is 2. So now in order to compute the result of f of 3, we have to do f of 2 times whatever old x is. Same thing, in order to find the f of 3's value of old x, we look in its allocation on the stack, and it's 2. What did I miss? Oh, sorry, old x is 3. Old x is 3, sorry. Old x is 3, reading problem. F of 2 is 2, old x is 3, and so we actually finally get 6, the correct value for f of 3. Questions on that? So let me show this a little more conceptually. This is kind of the line by line. All that happens when you have, even if we've got a program like this, where we have f calling g, we have f calling g. Whenever there's a function call, it gets its own allocation of memory on a stack, and any nested calls are pushed onto the stack, and when that call finishes, that memory is effectively deleted, and both control of the processor is returned to F, and also the current state is restored by using the stack. So for factorial, for our first call, we pushed local state onto the stack for f of 3, and when we had a nested call, we paused computation, left its state on the stack, and went to go compute f of 2. In order to compute f of 2, we had to pause computation, save its state onto the stack, and then go and compute f of 1, and then eventually make a new call to f of 0, give it new space, pause f of 1, leave its state onto the stack. And so you can quickly see that if you don't have a base case, what's going to happen? This recursion is going to be unbounded. You're going to get a stack overflow, a classic stack overflow. And so because this version of f has a base case, that is, it has some branch, some path through it that doesn't make another recursive call, we know that it will terminate. Once it terminates, and this function terminates, we delete its state from the stack and return control back to whatever its parent call was. Once that finishes, we delete its state from the stack and return control to whatever its parent call was, and so on, until we finally get back to our original function call and complete computing its value. Questions on that? Make sense? Yeah.
Does main count as a stack frame?
Does what? Main?
Yeah.
Absolutely. Main is a stack frame, yeah. Yeah, so if we were calling main here, yeah, main would be the first stack frame for our function being called. And once f of 3 is done, main called it, it will restore its value back into main. And then main is also a function call, so once it's finished, its state will be cleaned up. And this is the loader that manages this. There's an entry point start in the program, and this is the C runtime. You're basically back into the system.
So for homework 15, you would have to include main as one of the.
What was homework 15? It's okay. Either way. Yeah, you can show either way. So yeah, to give a preview of the question, how many stack frames would you have? So if you include main or not, that's okay.
So would a global variable be outside of all those?
Yes, global variable will be outside, and in fact, I think this is. Let me see if this is skipping ahead a bit. Where is it? Is it here? There's a really good diagram that I think this is it. Yeah. So this is your binary, this is your executable file. this is your actual program binary. Did you learn about this in the stack versus the heap? Who learned about stack versus heap in computer organization? Okay, I think everybody should learn about that. So your running program has stack and heap, and heap is for like malloc, for dynamically executed stuff. Stack is for these automatically allocated variables from functions. And there's also usually a segment for statically allocated stuff. I guess that's this. Well, I guess it's here. Yeah, I guess it's just put kind of in the heap, at the bottom of the heap. I think it's a different segment in the assembly file. But you basically have a segment for statically allocated stuff, and that includes global variables. That may also include statically allocated data like string literals will appear in this static segment. Yeah.
Is there a difference between like those global variables and like things you define like outside of the main function?
No, things you define outside the main function are global variables. Yeah. Yeah, you only have local and global variables in C. All right. Questions? Questions on this? All right, so I have another, let's see, so that's factorial. I have an example of this with Fibonacci. I think it's probably unnecessary at this point, but you're going to get the same problem with, I was going to explain it with this, but I think factorial this will be even more complicated. Let's see, all right. So we can do, all right, I'll just go over the slides as is. Okay, so this allocation of memory is called a stack frame. So it sounds like you learned in computer organization, every running program has this segment of memory called the stack. And what are the machine instructions for adding and removing data from this stack? What's that? Pop and push in the stack. Yeah, pop and push. So they're actually, and lots of machines have instructions for adding and removing data from the stack. Pop and push. They actually have machine instructions for managing this stack data. So the system and the processor are actually set up for having this kind of automatically allocated memory location at runtime, memory slots for variables at runtime. All right, so let me go into I'll start some of the details of how this actually works at the machine level, the kind of support you have at the assembly at the machine level. So just to get some terminology here. So the set of memory here that holds all of the state for a function instance is called a stack frame. It's a stack frame because it's not just one piece of data, it's all of the data needed for this function call. Sometimes called an activation record. So if you think of the function as being currently active. But it holds all the information you need to freeze the state of the function. So that includes local variables, but it also includes parameters, because parameters are just local variables. It also includes information in order to start resuming execution of the caller function. So I didn't make that clear here, but how is it that the processor will know where to continue executing in the parent caller function? And the way that's done is the address of the next instruction to start executing when you resume is also stored in this stack frame. And it also stores a linkage or a pointer to the parent's stack frame. So let me, let's see if I've got, yeah, okay, I'll draw it here. So in addition to data, each of these stack frames has a pointer to the parent stack frame. So why would we want to do this? Why would we want to have a pointer to the parent stack frame? Yeah?
So that when you stack, it knows where to return.
Yeah, exactly. So we don't have to know at compile time where the location in memory of this parent stack frame is. And in factorial, all the stack frames may be the same size because it's the same function. But when we go back to main, it might have a different size from factorial. So the way we get around this is we just store a little pointer called the base pointer that points back to the parent caller's stack frame. We also have a return address that points to the program counter that we need to restore in order to start executing the parent. Again, continue executing the parent. All right, questions on this so far? So this is the contents of the stack frame. Parameters and local variables, a return address, that's the next program counter to start executing. That's how you resume executing the parent. And also the stack frame of the parent. That's how you restore the state of the parent. Okay, so parameter passing is very system dependent. The easiest way to do it is to just push those parameters onto the stack so that the callee will have access to them. In x86-64, it's a little bit more complicated. They use a combination of registers and the stack frame. So we won't have to worry about this, or we'll let's see, I think this is in CoGen 2. Yeah, this is in CoGen 2. So we'll cover this a little bit more for the next project. But basically, the first 6 parameters are in registers, and the rest of them are on the stack frame. So this is the stack frame that x86 is x86 and the system 5. This is like the Unix convention for doing this. You have the first 6 parameters in registers, and the rest of the parameters are in the stack frame because, you know, they're just like local variables. They're stored in the stack frame. You have the return address, and then the RBP, this is the base pointer. This is the pointer to the parent's stack frame, and then local variables. So this is all by convention. This is the Unix world's x86 version of the stack frame. Different processors may have a different organization. Different operating systems may have a different organization. But the key here is that local parameters, local variables, the return address, and the pointer to the parent stack frame, the base pointer, are all stored in memory in this stack. Questions on this? So the details of this, we'll get into the details more when we get into parameter passing. It's a little annoying because in the 64-bit x86 version of the Unix world system called the System 5 application binary interface, the first 6 parameters should be passed through registers. And why would you want to do that? Why would you want to pass parameters in registers instead of the stack? Yeah. Well, they're all easy to access, right? I mean, they're the memory. You have access to all the memory you want. You have access to registers, yeah. Registers are faster, yeah. I think that's their reason, is performance reasons, that you'll just have faster function calls to do this. It's just something we have to deal with. I'll give you some code to help deal with this. But okay, so that's how we pass parameters. All right, just to finish up, so here are some of the key assembly things to know. So there is a special register in the Intel world just for storing the base pointer. And so this register is meant to always hold the current stack frame, a pointer to the current stack frame. And so while functions aren't directly executable in Intel assembly, they do have special registers and instructions to help you, the compiler writer, generate code that will correctly implement functions. And a couple pieces of support they have is a register that is supposed to hold the current stack frame's pointer to the current stack frame. Yeah.
Is that what you would use the pointer arithmetic to do, like go up and down stack?
Exactly. Yeah. So that's what you would base off of. So in order to find local variables, you would have an offset from the base pointer. You can think of it as a pointer to an array. And when you want to find local variables, they're an offset from that pointer. So it works just the same way. And you can see at the processor level, you know, what pointers and arrays really look like at the operational level. There's also a register that's always supposed to hold the stack pointer, or that really does hold the stack pointer. Now I say it's supposed to hold the base pointer because if you make a mistake as the compiler writer and mess up the management of this pointer, this register, it may not hold the stack frame, the correct stack frame. or the stack pointer may not hold the correct stack pointer. And actually, there's some security ramifications to making this mistake in coding or in the compiler to allow the machine to get into a state that doesn't actually return to the function that you want it to return. There's also a call instruction, which isn't like call in the C function world, because it's not going to pass parameters. It's not going to create the stack frame for you. All it's going to do is going to save the return address for you, which in the x86 world is called the IP, or the instruction pointer. That's the same as the program counter. It's going to save the next address for you. It's going to save the return address, and that's it. And then it's going to branch to the function's address, the function's label. So all this is a branch instruction. You give it a label, and it'll branch to that label. But before it branches, it saves the return address for you. So you could certainly do that on your own. You could just push the instruction pointer, and you could just do a branch. But call does two things for you. But it does not do parameter passing, does not do return values, so it is not like an actual C function call. And then you have the kind of converse of that, the return instruction, which pops whatever the address is, or whatever the data on the stack is. It pops that off and branches to it. So you could also do that with two instructions yourself. You could do pop and then branch to that address. This does the opposite of call. Call pushes the next address, the return address, and branches. This pops that address and branches to that address. Questions on that? So this is really all the support you get at the machine level for implementing functions, and then it's up to us as the compiler writer to generate the correct sequence of instructions that will set up all of this memory for us. And just to kind of reiterate again and again, your compiler is not creating these stack frames. Your compiler is creating code that at runtime will create these stack frames. This is the kind of confusing part of compilation. We're not computing the result, we're generating code that will compute the result at runtime. And when we get into functions that at runtime create allocations of memory, generating that code can get kind of tricky in the compiler. All right, so actually 3 minutes left. So let me finish covering this. I look like some people are eager to leave, but just to some more kind of definitional stuff. We'll get into the actual assembly next time. Whenever you generate code for the function, by convention, the beginning of the function always has a prologue, which sets up the rest of the stack, and an epilogue, which tears down the stack frame and returns. Yeah.
So kind of like a pre and post condition in a sense?
Yeah, kind of. Yeah, they do actually enforce a pre and post condition on the memory on the stack. Yeah, they enforce a pre and post condition. So the epilogue will set this stuff up here. The prologue will set up this stuff here. It'll save the old base pointer. It'll set up local variables. And the epilogue will tear these down and then call return. So just also as a little preview, because the caller is what has access to the parameters, the caller sets up this part of the stack frame. So this stuff in green is what the caller sets up in the stack frame, because it has access to the data for the parameters, and so it passes it, also knows what its next return address is. So this half of the stack frame is set up by the caller. The call instruction is made, the return address is saved, and then it's up to the callee in its prologue to set up the rest, including saving the base pointer of the parent, setting up local variables. And then the epilogue does the inverse. The epilogue tears down this stack frame, restores the base pointer to be the parent's base pointer, and then calls return in order to pop this return address and go back to the caller. All right, questions on that? Yeah.
Would you recommend that we start working on the code one soon?
I think you can look at it. I haven't shown the assembly code yet, but it's in there. It's in that instruction. So by all means, you can start working on it. Get the project set up. That's why I tried to put up a little early, so you can actually start getting the development environment set up. It's very much like calc. I've given you template code, and I've given you like all the code to generate and how to use Python. So sure, yeah, by all means get started on it. Yeah. There's only one file to create, just compiler/codegen.py. So here's the layout of the project. Most of this is given to you except for codegen.py. So you just do codegen.py. Here's skeleton code for it. And these are the only functions that you need to implement for this version of the project, and you'll have function call supported if you implement this correctly. And here's instructions for. We can go over that more next time when we actually talk about what the assembly looks like. But yeah, it works very much like the calc project. You use pip-n for having the shell. And all right, so it's 1:20. So thanks all. I think we ended at a good time. See you next time. How's it going?
I think I finished, but